So now let's talk about real-world examples of mole balance. So this is example problem 4.1. And the equation here is H2 plus I2 is in equilibrium with 2HI. So let's first set up our mole balance for H. So initially, we could have some hydrogen present as H2. And we should worry about the mole to mole ratio here because it is not 1:1. So for every mole of H2, there are 2 moles of H. There could also be some H present initially as HI, and the mole to mole ratio here is just 1:1. So there's 1 mole of HI per 1 mole of H. And we can set this equal to the exact same thing, but we'll switch out our I's for equilibrium. I'm just copying everything down. All right, let's substitute in our variables. We'll call H2X. Notice that these are all gases, so we definitely want to include variables for all of them. When we do that, we write this term as 2xi, where I indicates that it's initial, and we add in a zi term there. That's equal to 2x. We're not going to write EQ in there because 2x is assumed to be at equilibrium, plus z. Again, when you do your work, make sure to show in parentheses that this is in terms of hydrogen, and this is the equation that you would plug into Mathematica. And now let's go ahead and do this for I. I'm going to rewrite our equation. I could be present in both I2 and 2HI. So initially, for every mole of I2, we have 2 moles of I, and we're going to multiply that by the concentration of I2 initial. And then we could also have some I in HI. Set that equal to the right-hand side, which is our equilibrium side. Substitute in for our variables. Put I in parentheses. We end up with, let's see, 2 yi plus zi is equal to 2y plus z. And this is the equation you would plug into Mathematica. So what if you have something that looks really complicated? This is example problem 4.2. Here's the equation there. Carbon monoxide plus gaseous water is in equilibrium with carbon dioxide and hydrogen gas. In theory, we might need mole balances for all of the species present in this equation. Let's go ahead and write a mole balance for oxygen. So first, look at your equation. Let's see all the places where oxygen occurs. It occurs in carbon monoxide, water, and CO2. So we're going to have to write terms for all three of those. For carbon monoxide, you can see that we have a 1-to-1 mole ratio. So I'm going to go ahead and skip the mole-to-mole ratio and write in concentration COI. For water, you can see that there is a 1-to-1 mole ratio of water to oxygen. So I'm going to skip that and write concentration water I. For CO2, however, you can see that there is a 2-to-1 mole ratio of oxygen to CO2. So let's write that in. So for every 1 mole of CO2, there are 2 moles of oxygen. So we're going to write 2 CO2I. For the right hand of the equation, we'll write out all of the exact same things, but with EQs. Perhaps you can hear my children yelling in the background. Good times. All right, so then let's assign variables to everything and give carbon monoxide an X. Water can be Y, CO2 can be Z, and what in the world do we call H2? Let's call it W. That sounds good to me. All right, so when we substitute in all these variables, we get Xi plus Yi plus 2Zi is equal to X plus Y plus 2Z. And let's put in parentheses that this was for oxygen. So this will be the equation that we plug into Mathematica. How about we go ahead and quickly do a mole balance for, I don't know, do you want to do carbon or hydrogen? Let's do hydrogen. So for hydrogen, it looks like we will have 2Yi plus 2Wi is equal to 2Y plus 2W. That can be another equation that we plug into Mathematica if we need to. So if you don't see where all of these things come from, you should go ahead and on your own work out all the mole-to-mole ratios.